Alrighty, welcome to our latest episode of the exciting world of BCIT's TTED 4060. And today we're going to be talking about audio circuits. In our last video, we talked about designing and building a little project called the Erie, based around the TL082 op amp. And I'm actually monitoring that using our DP Scope SE. And if you look right beneath me in that window right there, you'll see my voice vibrating around as the sound is being picked up not only by this microphone right here, but by a microphone on a circuit board on my desk, and it's being amplified there, and that's what's feeding back into the DP scope. So today we want to take a look at a really nifty circuit that's been published online, and I've had students make it for years, and that's called the LED Color Organ Triple Deluxe. And so if you just Google Color Organ Triple Deluxe, you're going to come up with the schematic for it, and it's up on Instructables. And the author's done a really good job of going through and documenting it with some video and showing you how to lay it out on a breadboard. That's what we call them. You'll notice it's a little dated. Look at the eye device being used in there. But always nice to use something a little less expensive when you're laying out these circuits, because I have had students make the mistake of hooking up the audio inputs to their power supply. Usually doesn't end well for the audio input. You've seen a couple of phones and a couple of computers thankfully not get bricked entirely, but their audio output and their amplifier circuits have definitely been damaged. Anyway, as you go through the circuit, he's got all the parts listed out here for you, and the schematic, and just a really, really great guide on how to set it all up and how it should work, and some good comments down at the bottom where they discuss how it works. So LED Color Organ Triple Deluxe, and if you're looking for something a little fancier, he's also published the Color Deluxe 2, which has more LEDs and certainly better precision on picking out the sounds. This is a fairly introductory color organ. It's got a lot of simplifications going on, and you can certainly make more precise filters. But as far as a little project that you can do with high school students on a breadboard, I think it's great. And it's pretty easy to translate from the breadboard into proto board and into a genuine printed circuit board as well. So it's a neat project for doing with students. It's a suitable level that somebody, maybe not brand new to electronics, but somebody who's ready to take a step up and make some really cool blinking lights is probably ready for. Now, in order to understand what's going on with this circuit, you need to understand a little bit about sound. And that was why I thought it would be good if you had the Erie all hooked up so that you could take a look at things in real time. And you could say, oh, let's see what happens if I, let me just adjust my Windows, bring that one up in the priority here. And if I have a circuit all hooked up, and I can actually capture sound as the sound is going along, and I go, ooh. Now, we've got a couple of things going on right in there, and you can see that there's frequency. So if I can't whistle. It's like a super weakness of mine, so I can't and give you that. But actually, you could even see even that was coming up with a little bit of a very high frequency but low amplitude. Yeah, that's about. I can't. We'll get into better sources of sound later on. I've got a source of sound for you that's not going to get bricked or anything like that, but now you can see that sound bouncing around there. And if you go for a lower frequency, then you'll see that those wavelengths go further apart, because that means a lower frequency means a lower frequency of vibrations. Fewer vibrations per second are coming out of my sound box right there, vibrating the air and going through and hitting the speaker. And the other thing that's happening in there is the amplitude. So if I talk really loud and get really close into that little speaker down there, or microphone, I should say, if I get really close to the microphone and I go, ooh, you can see that the amplitude increases. So we got a couple of things we're looking at. We're looking at the amplitude of the sound, we're looking at the frequency of the sound, and then we're also looking at the waveform of the sound. And then to make things more complex, when we're dealing with real sounds like voices and music, we've got a whole bunch of these waveforms with different frequencies and different amplitudes laid over top of each other. So we're going to take a look at a little bit of that because the Color Organ Triple Deluxe helps us sort some of that out. Anyway, I'm just going to swap my windows around here for a little bit, and we'll take a look at a couple of interesting sounds. Okay, there we go. We're back up and running. I've got the screen swapped around here, so we can take a look at this now. And the main screen I've got up right down beneath me right here is a program called Audacity. It's an audio editor that I've been using for quite some time. And I've used this to put together an audio track that tells you what you're listening to. It's a two-note harmonic sine wave featuring notes C5 and C8 at 523 hertz and 4,186 hertz. And then it plays the sound. And while you're listening to that delightful sound, you can kind of hear that there's two things going on in there. And let's just stop here for a second. Let's zoom in on the sound. At the beginning, you can see the sound of my voice where I introduced what we were going to be listening to. And if I zoom in a little closer and come in right here, we can still see everything's packed in there really closely. I need to keep zooming in. And there we go. As we zoom in right here, went just a little too far, you can see the waveform that exists in the computer. Now, there's two sides to it because this is a stereo signal. So we've got a left channel and a right channel. Most of the stuff we're going to be talking about today will be mono. So usually when you talk about mono, you'll talk about looking at the left channel. But in here, it doesn't matter. We're just going to take a look at one channel. And what we've got is we've got two waveforms coming together right in here. And so you can see the low frequency waveform is creating this big sweep that runs along right here, while the high frequency waveform is bouncing up and down right in here, creating this waveform right here. Now, these two sounds are overlaid with each other, and this is actually a really common thing that is done just because it sounds a heck of a lot nicer than a single tone. Nature doesn't really go for pure tones. That's uh, maybe a bit of an overstatement, but anyway, what we've got happening right in here is we've got these two mixed together. And a lot of the times in electronics, what we want to do is we want to be able to mix signals together so we can send them down a single wire or over a radio antenna, out a single antenna, or we want to be able to receive a mixed signal and remove what's could be thought of as a carrier wave from the data wave in some cases, or in our case, we want to be able to pick out the low frequencies from the high frequencies so that we can blink lights, because if you can blink an LED, you can rule the world. So let's take a look at ways we can do that. And believe me, there are much more complex ways, okay? There's active filters and all that. But to take a look at the introductory way that we can do a little bit of this, let's go to Falstad Circuit Simulation. It's on that side. It's mirroring me on the screen. All the way over here. Let's take a look at Falstad's Circuit Simulator. And I've brought you to this website before a couple of times, falstad.com/circuit. And under the circuits in there, you'll find that he's prepared a whole list of passive filters. And we're going to take a look at a high pass RC, resistor capacitor filter circuit. Okay, so what we've got happening right here is we've got our sound over here, and you can see that the sound is changing frequency. Okay, and it's increasing right now. So it starts off with a low frequency sound, and then starts building up. Now, because this is an online web simulation, you don't actually get to listen to that. I mean, I could, yeah, I'll provide that for you, but it's probably not one of those bonuses that get requested a lot. So here we go. You can see it starts out at fairly low frequency and then ramps up to higher and higher frequencies. Now we've got two things going on in here. We've got a capacitor right here and a resistor right here. And then we've got a signal coming out at the other side. So on this little oscilloscope view right here, this you can see when I put my mouse over top of that oscilloscope that the input signal turns blue. Okay, so this is our input right here, and this is our output right on this side. Okay, so you can see that the output turns blue. Now, what's happening right here is we're providing a constant amplitude of input. Okay, so you'll notice that the peak to peak stays the same on the input side of things, but on the output side, when we're at low frequencies, look at how low that goes. Now we're going to start increasing the frequency because it's ramping up and going faster and faster and faster in here. And watch that amplitude on the output side as it starts to go up. And when it finally reaches a very high frequency, we're almost up to the full amplitude. And then as it slows that frequency back down and ramps back down again, the low frequency sound barely makes it through at all. Now, why is this? Well, as you'll recall, capacitors do not allow direct current to pass through them. The only time you see a signal pass through a capacitor is when it's changing, because this little gap in the middle represents our dielectric, which is a really high value resistor. It's impermeable to the actual flow of electricity. What's happening is that we're putting current on this plate, charging this plate up, and forcing charge off of this plate. And we can keep doing that until the capacitor gets fully charged. And once the capacitor is fully charged, it pushes back against the voltage that's coming in, and you don't get any voltage flowing through it. So in order to get a signal through a capacitor, it needs to be constantly changing. And a low frequency signal doesn't change very much. So when we've got that low frequency signal, there's enough time for it to charge that capacitor all the way up, and the capacitor says, that's it, I'm blocking you. No more voltage is getting through, no more currents flowing through this way. And so the signal coming out the other side becomes very weak because now you've got very little current flow coming right here, and it can pass through that resistor and go down to ground. So we've got this changing input and we've got a changing output, and only the high frequencies can get through this capacitor. Okay, so that's why this is called a high pass filter. High frequencies can make it through the capacitor, low frequencies cannot. Now, if you change the value of the capacitor, you're going to change the frequencies that it filters out. So for instance, if we put a 1 microfarad capacitor in here, okay, 1U, okay, there we go. Now our charge is starting to come through there. And you can see that it started to ramp up quite a bit sooner than it did before. And now that we're up to high frequencies, that capacitor is basically transparent to them. And now we start ramping down, and it's got to go quite a bit lower before we actually wipe everything out. Oh, sorry, 1U? 1U is going to respond faster. We were at 10U before. So yeah, we've got 1U is going to respond a lot quicker. So you need a higher frequency to pass through that than you did through the 10 microfarad capacitor. Okay, let's try this. Let's go up to a bigger capacitor and go up to 100U. Okay, and now slower signals will be able to make it through there just fine. And you'll notice that when we come down to the low frequencies, it doesn't ramp them out quite so low. There we go. We're still getting something through at the 20 hertz signal. And as soon as it starts to ramp up again, poof, there we go. It's coming up a lot faster because it's a lot easier to pass a low frequency signal through a high valued capacitor because it takes longer for that capacitor to charge. So the bigger the capacitor, the easier a low frequency signal can pass through it. Now, of course, that works in conjunction with the resistor here, okay, and that's why it's a resistor capacitor time constant. If you increase the value of that resistor, you're going to you're going to mess around with the voltage on there too. So let's just try increasing that to a 350 ohm resistor and see what we get coming out on the other side. And now in this range of filtering, okay, well, we're still getting 5 volts there. We played with this, we unfortunately automatically changed the scale when I changed that, but now we come down here. And even at our really low frequencies, we're still getting 4.7 volts coming out of there. So there's hardly any filtering at all taking place at these frequencies because we've really lowered the frequency that is that we're cutting things off at. Later on, we'll talk about some of the formulas on that, but it's important to just take a look at this and understand that high frequencies pass through a capacitor quite nicely. So when we're looking at a signal like this one right down here, where we've got a mix of low frequencies and high frequencies, the high frequencies should be able to pass right through that capacitor, and the low frequencies should be filtered out by it and blocked. And depending on the value of the resistor and the capacitor, that will determine which frequencies are being filtered out and which ones are allowed through. Now, let's take a look also at the passive filter. He's got a low pass filter right here. And believe it or not, the low pass filter also involves a resistor and a capacitor, but they work just a little bit differently. And you've actually made a low pass filter before. This is the same as what you had on your power supply to keep the power nice and smooth on the output side. Because any high frequency changes that happen on there are going to pass through the capacitor, and where do they go? They go right back to ground so that they're not coming out on your output signal. So now the only thing that's coming out on this side, in case of your power supply, is nice smooth DC circuit. In here, as you watch the frequency go low, and here we are down at fairly low, you can see that we're getting all of our signal basically coming out because we've got nice smooth right here. We've got time to charge this capacitor, so it holds that voltage. But now as we get to faster and faster signals, okay, they're coming in here and they're trying to budge the charge on here, but they're going back and forth so fast that they never have an impact on there. So that's our resistor capacitor filter circuits. We're going to use them a lot in the circuit, so I just sort of wanted to get you thinking about them, see them in Falstad right there, and get the idea that a high frequency signal can pass through a capacitor very easily, and a low frequency signal can't pass through the capacitor. If you take your high frequency signals and run them through here, then your high frequencies go down to ground and they disappear, and you get the low frequencies coming out. But if you put the capacitor up here, then the high frequencies can pass through and the low frequencies are blocked. When you put them together, you end up, see if he's got a fancy bandpass filter with a coil in here. Coils work great, and you start getting into, like I say, you get into all sorts of fancier filters in here. I was just going to take a look. No, he's got fancier and fancier filters going down on here, but not just a resistor capacitor bandpass filter. That's all right. We'll talk about them in just a minute. Ooh, better not choose that one. Let's see. There we go. So here we go. This music's from bensound.com, and it's free. It's open source. They make it available so long as you say nice things about them in your video. So thank you, bensound.com. If you're looking for a good place for free or open source music to listen to, go check out Bensound. And so anyway, here we go. We've got our color organ flashing away, and the lights might look a little bright coming in on there. I'm deriving my audio from a little circuit called the DF Player Mini. And I've got a micro SD card on board the DF Player Mini, and it's driving a speaker right down here on my big bad breadboard board. And I can control which piece is being played and the volume of the piece by pressing these two buttons right in here. So press it once and it restarts. Press that, I get the next piece. Press one and hold, and it gets louder. Press the other one and hold on, and it gets a little bit quieter. So neat little device, easy to set up on a breadboard. And just remember that if you're hooking that up, it runs off of 5 volts. So really critical that after you've hooked your TL082 up to a 9-volt source, that you have 9 volts on one side of your board and 5 on the other, and that you don't end up getting those two mixed. Before you plug things in, I'd say check to make sure that your 5-volt rail and your 9-volt rail are both at 5 volts or 9 volts as appropriate. Otherwise, you'll end up toasting things. So down in here, we've got the Erie circuit. This is our little electret microphone, and that's picking up the audio. And this is kind of ugly breadboarding. If I was to go back and redo that, I'd change the orientation of the chip so the power supply was on the 9-volt side. But anyway, and then this is just a little line I've hooked up for an audio output, so I can read that on my DP scope, and that's where our bouncy little DP scope signal right down there is coming from. Alrighty, so what's going on in this circuit right here? The DF Player Mini is generating an audio signal for us, and that audio signal is coming over to a resistor right in here. Now, I'm gonna just turn this off for a second here. And let's take a look. If I blow this schematic up a little bit larger, we'll be able to talk about what some of the things are doing right in here. Okay. This will do just fine. There we go. Guess I could have pressed pause while I was doing that, but no worries at all. Alrighty, so now in this window right down that way, somewhere over there, darn mirroring on the camera, you can see the schematic for the color organ triple deluxe. And the schematic is designed to have 2 different audio inputs on it. So it comes in right over here, and this one is also designed to work at 9 volts. So we'll take a look at that in a minute, but we're only going to use one audio signal. We'll use the left channel in this case, or you could use the output from your Erie. Either one, you can run into that circuit. And so you're going to start on this circuit right over here. Pick a nicer pen. Let's see, and you're going to have some kind of waveform coming in right here, bouncing around, but it's coming in this way, and then it's passing through a resistor, and it's coming to a capacitor right here. Now, there's a neat little circuit right in here that is worth taking a look at in its own right, okay? Because right here we have an NPN transistor, and so at the NPN transistor, the emitter is hooked into ground right here, and there is a resistor coming into the collector. Now, an NPN transistor will turn on and it will allow flow if we have a voltage about 0.7 volts or higher right here on the base. Okay, now this is a really important part of this circuit, and we'll take a look at what it looks at on the DP scope in just a minute. But what's going on right here is that this is up at 9 volts. Each of these symbols represents your 9 volts. And then because it goes through this 1 k ohm resistor, if your NPN transistor turns on and starts to conduct, then electricity flows down here and you get a voltage drop across the 1K resistor. And when you get a voltage drop across the 1K resistor, this means this entire line up here drops from 9 volts down low. And that's what drives the 3 different stages, the high frequency, mid frequency, and low frequency stages of your circuit. So this is a critical first step to making sure that everything's working. Now, because the voltage at the base revolves around zero point 0.7 volts so closely. You know, 0.7 volts for a lot of our silicon semiconductor devices are a really important number. We want to set the what we can call a bias voltage right on that base so that the base is sitting at 0.7 volts when there's no signal being applied. That way, if we get a little bit of a positive signal, it goes above 0.7 volts. And if we get a little bit of a negative signal, it goes below 0.7 volts. So we got to have it sitting at 0.7 volts to make sure that it's all working okay. And to do that, we bring in this diode right here. Okay, and this little blue diode, there we go, I marked it right in there, D1 in the circuit, means that what's going to happen is that at this point in the circuit right here, okay, where that connects together, you've got a voltage divider, another voltage divider. And the voltage divider is between this 10K resistor and the diode, which means that you're going to have 0.7 volts at that point right there. Now that 0.7 volts doesn't get applied directly to the base because otherwise it would take a lot of current to change that. It runs through a 10K ohm resistor. And so now a little bit of signal coming in on this side. Okay, so you you change your signal. Okay, the voltage goes up. You charge up this side of the 10 microfarad capacitor plate. That forces charge off the other side. It's got to go somewhere. It's got to go through the transistor. That raises the voltage on the base just a little bit, and it allows the transistor to start conducting. If your sound wave's on the negative side, though, and you're discharging this plate right here, okay, because your voltage has dropped from what it used to be, now you're pulling charge off of the first plate, which means you have to put charge onto the second plate. So now this capacitor is sucking voltage in this way. It's sucking charge in this way, and that's pulling the voltage on the base down. So the transistor stops working right here. So the nature of our sound wave, when we're up at the peak part right here, when we've got this rapid climb and we're putting a lot of charge in there, that charge is coming here, it's charging up this plate, it's forcing charge off of right here, it's driving up the voltage, and it's turning on the NPN transistor. When the NPN transistor turns on, there's a resistor right there causing the voltage right here to drop quite low, and that generates a signal that goes out and drives our other stages of our circuit. So let's just take a look at what that looks like on the well, on my implementation of the breadboard. I've laid mine out a little bit differently from the DP Scopes author has laid out their board. Right. Ooh. I've got two screens going on right here, and I sometimes confuse myself whether my mouse is on the screen that's being captured or on the screen that's doing the movement right here, and you don't actually get to see that until I hit the transition button. So there we go. We've transitioned now. We've got the right screen showing right in here. Now, I was playing around with this and trying to fit things in really neat and tidy, but I also set mine up a little bit differently from what you'll see in the instructions on the website. The instructions on the website are great. You hook it up that way and your circuit's going to work. But I hooked mine up a little bit differently because I wanted to be able to leave the LED all plugged in on my big bad breadboard board, or LCD plugged in. And I know a lot of you still have your Ardu circuits hooked up down at the other end of your board. So I'm trying to use the space as efficiently as I can. Now here I've got a DF Player Mini, and I've probably put a DF Player Mini into your kit. There's a little schematic for hooking it up. It's not so hard to do. And really there's not a lot of magic going on in there. And so our output from the left channel right here comes up through this blue wire. Okay, so where it says audio in on our schematic, that is our audio in right there. And here's the 100 ohm resistor, brown, black, brown, that it goes through, and it comes to this leg right here. And this is our 10 microfarad capacitor right in here. And so our 10 microfarad capacitor comes through right to here. And so now we've come up to about this point in the circuit. So I'm wiggling a pen around on the screen. You know what? I can make that a little bit bigger for you. Just hold on a second here. There we go. Transition. OBS Studio, very useful recording utility for a lot of the stuff that we've been working on right here. In fact, I think I can make that even a little bit bigger still. And bring that up one layer in the hierarchy. There we go. Okay, so as I was saying, we've come in right through here. We've got the 100 ohm resistor. That's this 100 ohm resistor right here. Going to highlight that in, oh, no, that's pink, just to say that we've already done it. Okay, and then we come to the capacitor, and let's highlight that in orange right there. So that capacitor highlighted in orange is this one right here. And really there's nothing else plugged into these pins right here. These are gaps in between the switches that I was trying to use efficiently. I'd originally designed to use this with smaller switches, but they didn't stick into the breadboard as well, so I had to go back and play around with it. Anyway, so now we come down right in here, and there is a 10 K ohm, brown, black, yellow, right in here. Brown, black, yellow. Is my lighting off? Should be brown, black, orange. 10K coming right down into here and meeting up with a diode, and you can see that the negative side, the cathode of that diode, goes straight into ground. So at the junction point of these two, I should have a 0.7 volt signal because of the 0.7 volt voltage drop across a standard silicon diode, and because we've got a resistor that will also have a voltage drop across it coming right in there. So that's the blue resistor right up here and the blue diode right down here. Now there is a 10 K ohm resistor that comes off of there, and that comes in to the base of the transistor. So let me just highlight that to indicate that, hey, we've got that 10 K ohm in there. And great choice of colors, completely wipes out what it is that we just did right in there. Okay, so now we're at this transistor, and the transistor is the first stage of the circuit, and it's a really important part of the circuit to get right. So here's our 1K resistor coming down from the plus 9 volt side. There we go. We've got that 1K resistor coming in there. And pay attention, that goes emitter base collector on a 3904 NPN bipolar junction transistor. Comes right in there. And in the middle of it, you can see that the 10K resistor comes straight to the base, and there's nothing else coming into that base right there. Okay, so that's that 10K coming in right there. There's also the signal coming in from the capacitor right here, because of course the capacitor's tied up here. We've just covered that in purple so we don't see it. And our emitter is tied into ground right in here. So we've got the transistor all taken care of. When a signal comes in from our audio source, in this case the DP scope or the DF player, it comes through the resistor, through the capacitor, okay? The capacitor will filter out any DC signal. It's a 10 microfarad capacitor, so it's going to let anything with any kind of frequency pass through, but DC or super low frequencies are going to get filtered out. That's going to come into the base of the transistor. The base of the transistor is going to turn the transistor on and off when you get a positive voltage come in right here. Turn it off when it goes low. And then on this side, you're going to have a 0.7 volt bias coming from this little voltage divider circuit and through a 10K resistor into here. Now, before you do anything else in your circuit, this is a great place to stop and take a look at what you can see on your DP scope. Because what you should be seeing is you should be seeing a signal coming in, and then you should see some voltages bouncing around. So I'm just going to change my DP scopes plug-in right here. And now it's just kind of wandering around randomly and picking up my finger. I'm going to plug that in to this line right here. Okay, so I want to connect right into there. Those holes are all filled up right in there. That hole's filled. There is one hole just behind that 3904 that I can plug into, so I can watch what the voltage is going to do right there. And like I say, all I've done is I've just clipped into a little bit of wire, and the other end of the DP scope is hooked up to ground right here. I've put a little capacitor across the power supply and ground lines. It's never bad to filter your power supply and ground lines while that's running. And now I should be able to turn on my DP scope or turn on my DF player. And let me come over here and bring my there we go. Let's bring that to the front and make this a little bit bigger so we can see what's going on with this voltage at this point. Okay, that's right in my face. There we go. Okay, let's come over here and should be running this. And well, let's. Okay, much higher voltages coming through right on there. Let's take a look at what's going on. We're going to have to change our vertical division here. There we go, 2 volts per division. You can slide the baseline for your DP scope around. And now we're starting to see some flashing in time with the music. Okay, I just had to check my levels and make sure you can pick up some of the audio going on here too. All right, so I'm just going to stop this for a second, and no, I didn't want to stop it there. There we go. That's a nice stop right there. So what we're seeing right here is we're at 2 volts per division, so 2, 4, 6, we're at 8 volts, which not bad coming off of a 9-volt battery. They've got some high internal resistance, so they don't always give you exactly 9 volts. And when we get that big pulse of music coming in right here, and it comes in and it charges up the move screens around on other screens. So when that pulse of music comes in and hits right here, forces charge off the 10 microfarad capacitor, drives it in here, turns on this transistor, and at this point right here, just down from that 1K resistor where it meets the collector of your Npn transistor, you should see a signal that looks something like this when you're running music into it. And that, somewhere, if you're looking at it, I'll often use 1 millisecond per division when looking at audio signals. And you should see this coming through right here. Oh, just a minute. YouTube's going to nail me for copyright if they hear that. Hopefully I've been talking over it enough, but bend sound. There we go. I'll harass you in class with the continuous stream of ABBA for the next couple weeks. And here again, you can see the multiple pulses coming down because we're getting higher frequency sounds coming through there and driving it in here. So if you're not seeing a signal like that, then your circuit's not going to work. Okay, now that's what's coming in on the, or that's what's heading out of the transistor. You can also take a look at what's going on at the base of your transistor. So if I change my plug-in right over here, so that's in line with the base now, you're going to see something quite a bit different right in here. And what you'll, let me zoom in a bit on that. So you are going to see a signal bouncing up and down. Sometimes it actually goes below 0 volts because, of course, you're sucking voltage back into that system. That's okay. It just turns the transistor off a little bit better. And right here, I'm at 0.5 volts per division. So tell you what, let's go down to 0.1 volt per division. Okay, and now if you take a look in here, so I'm at 0.1 volts per division, and if this is 0.1, 2, 3, 4, 5, 6, 7, this line right in here is my 0.7 volts per division. And when the audio exceeds that line, then that's when the transistor should be turning on. Okay, if I stop the music and everything settles out, then I should see a nice, smooth 0.7 volt line on there. And that's that base of the transistor just sitting there waiting for a pulse to come in and turn it on, or for the receding pulse to go back and confirm that it gets turned off. So really important part of your circuit. If you can't see signals like that coming in to that first transistor, the rest of your circuit is going to be hosed. It's not that hard to get the first stage right, but it is worth using that DP scope that you spent all the time building to stop and check and make sure it works. And of course, if you're in the lab, then you've got regular oscilloscope to hook up and you don't need to use the digital one. But the digital ones work great for troubleshooting this circuit. They're pretty hard to troubleshoot with just a multimeter. Okay, so let's carry on right here. Let's take a look at the next stage that we're going to go to on this circuit. And I'll bring up, yes, this window right here. Make that big again. There we go. And move it up in the hierarchy and transition. Okay, there we go. So now we've seen the signals that should be coming in at this stage of the circuit. And that should be coming out. And in here, I've used a yellow line to mark that up. So I'm just going to go over and I'm going to draw this entire thing in yellow because that's the color that I've used for this line all the way through. So this signal comes to our high frequency, our medium frequency, and our low frequency LEDs. Okay, and let's take a look at what happens at our high frequency setup first, right in here. Well, remember we said that you have to have a high voltage, or sorry, a high frequency to pass through a capacitor. Just going to move this over a little bit here. There we go. You've got to have a high frequency to pass through a capacitor. So naturally, the high frequency side of our circuit is going to have a capacitor right here, and it is going to be a fairly low valued capacitor. Okay, so it is a 0.047 microfarad or 47 nanofarad capacitor. That capacitor is going to charge up and discharge really quickly. So unless you're sending really fast signals in and out of that capacitor, it's going to block them all. So all of your lower frequency signals are still going to be out here in this yellow line, but they're not going to be allowed to pass right through here. Now, this side, the author of the circuit did a little bit of a trick. Instead of putting this voltage down to ground, he put it up to +9, which is a fixed voltage and can actually absorb any signals or any noise that makes it through there fairly quickly and fairly easily. But because he used a resistor to do it, it can't get all of it. So when you suddenly get that big downward spike in your yellow line out here, when this capacitor or when this transistor turns on, okay, and now you've got this voltage drop, this line drops down to a very low voltage. That pulls charge back off of that capacitor. It pulls charge off of in this direction. And this is a PNP transistor. Okay, notice it points in proudly. And a PNP transistor works differently than the NPN. The PNP turns on when current can flow out the base. In other words, when you take your finger off or put a lower voltage onto the base, then the transistor turns on. And when the transistor turns on, in this case, the LEDs turn on. So to get these LEDs to turn on, you have to send a high frequency signal so it passes through the capacitor right here because it's a fairly small capacitor. And when it passes through that capacitor, it pulls backwards on here, turns on the transistor, and allows current to flow down through the LEDs and out the current limiting resistor. Just to get, you can play with those values of the resistors. You can play with the types of LED. Yeah, there's lots you can do on the circuit once you're going here. We're not really maximizing everything, but that's what's happening right on that circuit. Let's take a look at how this is all laid out on the board. Okay, and just shrink this back down a little bit. Move it back to the side over here, and there we go. So where is all this sitting in our board now? Okay, now most of our signal is going to come out on this yellow line right in here. But because this is the first stage that we're going to, we don't need to jump to anything with a yellow line. And in fact, there's that little 047, yeah, U047 or 47 nanofarad capacitor right in there. And you'll have to do the math to figure out what number a 47 nanofarad capacitor has on it. And the signal's going to come right through here and pass right into your base. So you can see this is a 3906 Npn transistor, and the signal comes right through this capacitor into the base right in here. And okay, not quite as good as the camera I got at work, but we're making it happen here at home. Okay, so that signal comes right into there, and you can take a look at both what it looks like on the side coming in and on the base side right here. And let me turn that back on. There we go. Oh, and our voltage is now gone up and off the display. Okay, now the voltage we're seeing right here, okay, is fluctuating around. I'm at 1 volt per division. So it's 1, 2, 3, 4, 5, 6, 7. This is 8 volts. This is about our rail voltage. You can see sometimes it spikes above it. That distinctly turns that capacitor off, or that transistor off, sorry. An NPN transistor needs to have its voltage drop lower, so it's only when it sees these little spikes coming down that it flashes the LEDs on. So we've got that coming in right there, and then you can check the voltage coming out on your LEDs. Just pressing stop here to try and catch a couple of nice spikes is coming out right here. So when we get high frequencies passing through there, the transistor will have one of those little drops on the base voltage, which will turn on the flow of electricity through the transistor and create a spike coming out from the collector, which will turn on the LEDs. Okay, now where a lot of people run into some problems on this circuit, they'll put their LEDs in backwards, and you'd think you would have learned on the Winky Blink, but it's been a while, so make sure your LEDs are in the right way around. Sometimes people will have 3904 instead of a 3906 in here. Sometimes they'll have it plugged in backwards. So you need to make sure that you've got the 9-volt line coming right down in here into your emitter of your transistor, and your signal coming into the base, and that you're using the collector to drive the LEDs. Okay, so on our little circuit right here, we've now, what color did we use? We made those yellow LEDs. Let's highlight them in yellow. Those are the two LEDs that we just looked at, and their associated resistor. So I've hooked one into this row, one into this row, and there's the resistor going off to ground right in there. Those are the ones that we've just highlighted. And then we've got a 2.2K ohm resistor plugged in right here, coming straight down from 9 volts or 8 volts or whatever that signal actually is, right into the base. So that is, let's choose a different color. Let's make that one orange. So we just put the orange one in there, and the orange signal meets up with the signal coming in from the 047 right here, the blue marked capacitor on our schematic. And that is the secret to our first stage. So if that's all working, you should be having yellow lights or whatever color you chose to put in for your high frequency blinking away for you. Okay, we'll move down the circuit a little bit now. And now I'm actually going to jump ahead all the way to our low frequency because it's just a little bit easier, and it's a really nice contrast in relation to our high frequency side of the circuit. Because in our high frequency side of the circuit, we had a high pass filter. Very clearly, high frequencies can go through that blue marked capacitor, and they work together with this resistor, and that resistor and that capacitor create your filter. Over on this side, it's a little bit different. Okay, in fact, the resistor and capacitor have swapped positions because it's a low pass circuit. Okay, so on this circuit, okay, our signal comes in right here, and any high frequencies can pass through this capacitor and just come up and disappear into the power rail. So our high frequencies are going to be disappearing on this side, and our low frequencies are going to be coming in here and turning this transistor on and off and driving these LEDs. So let me just jump ahead down here to our low frequency side of this circuit right in here. And I've got red LEDs, so I'll highlight these ones in, well, this is as close as they give me to red. And wouldn't it be nice if I had some nice magenta LEDs in there to do this trick? But we'll fill in that section in magenta for our two red LEDs right here. Now I wanted them a little bit brighter, so right in here I used a 100 ohm resistor instead of the 270 ohm resistor. It's also quite possible that I forgot to pack a 270 ohm resistor into my own kit. So anyway, yeah, as with a lot of this stuff, if you play around with the value and you go for something that's right nearby, you're not going to cause a great amount of havoc, except for those times when you do. Same thing in here. If you don't have the exact value, now don't mess around with the third band because you'll be off by an order of magnitude, which wouldn't help you much at all. But if you're, if you're off on the second band or something like that, it's not a big deal. Use something close, and what you'll get is a slightly different frequency on your filters. And in fact, since you're doing this on a breadboard, you can go back and you can change some of these capacitors and resistors so that you can maybe get a bit more differentiation in your music. So if you listen to a genre of music that happens to have very fine gradations in pitch, then maybe you need finer gaps on your um, filters. And if you listen to something that's got music tones all over the place, maybe you want broader gap. Anyway, another PNP transistor right here, so another 3906 sitting back right here. Once again, the emitter is connected straight into the positive line. And in between there, well, let's take a look at the various things. We've got a 2.2 K ohm resistor filtering out the circuit that comes in, and a 2.2 K also filtering out to the top right here. So let's highlight these one at a time and take a look at them. I'm just going to put some yellow on this one right here so we can see where that one is sitting on our circuit, and that's running right in here. Okay, so there's your positive connection that comes down right there. A little hard to tell from up above, but that comes into the base. And also connected to it is another 2.2 k ohm resistor right in here. Okay, and that one I've just folded up on end and done a little jump right over top of the positive line that's coming into the emitter. And we've got a 1 microfarad aluminum electrolytic capacitor that I've done a nifty little trick to. Instead of jumping it all the way over to the positive line right here, I've already got positive running in right here. So I just put it into the same pin that the I always have to look this up and make sure that the emitter is plugged into. I don't know why I have to look that up, but I do. Okay, so mainly because I don't want to say it wrong. Mainly because I don't want to go edit the video if I do it all wrong. Okay, so there we go. That's coming in right there. There's our emitter. And since that's already hooked up to a positive line, I can just run that capacitor in right there. It's a little 1 microfarad, and it's just going from the base to the emitter, which if you look right here, I'll pick a new highlighter color for it. And if you look right here, we're talking about the green capacitor right there. It actually does go from the base to the emitter, just the emitter's hooked up to plus 9 as well. So if that's all working and running well for you, let's plug in right here. And your signal, it should be coming in through this yellow line that I've jumped together. And you can see that the yellow line comes out through here, jumps right over here. And if I play a bit of music, there we go. And let's run the oscilloscope right here. There is our yellow line signal coming through there. And you can see it really going low. And you can see longer pulses where the hand claps come together because that's kind of your baseline. They're not as frequent. And then you get some of the short little high frequency ones as the bells or chimes start sounding in there. And so that's coming in and that's getting filtered out. So if we take a look at the bass, make sure I plug it into the bass. I think that's going to be the bass right there. There we go. So the signal looks a little bit different right in here, whereas on the high frequency side, we're seeing a whole bunch of short little bursts. If we stop right in here, you can see that now we're getting longer but smaller bursts, okay? And they don't happen as often because this is the low frequency side. And coming out over here, when we're running the LED, there you can see the blasts of light going out to the LED, and I'll stop it right there. And it never wants to stop. There's a nice little blast of the LED coming on, turning on, but then it's off for quite a while. So the LED's on for a little bit longer, and then it's off for a little bit longer because we're on a lower frequency side of the circuit. So on one side, we've got our high frequency filters, and on the other side, we've got our low frequency filters. Now let's go back and take a look in the middle where we put them all together. Okay, now in the middle of the circuit, right in here, we've got this bandpass filter thing hooked up, and it's a combination of the two. So there's two capacitors in here and two resistors involved in the circuit as well. So we've got a resistor coming in right here. So we've got a 1K ohm resistor, and you can see that 1K ohm resistor on the breadboard because the signal comes in for this circuit. It comes in right here. And then I could have just had this one stand up and do the little loop over thing, but I lay it down so that you can see the brown, black, red, confirm that it is a 1K and that it comes in right to here. Now that 1K doesn't go straight to the base. It has to go through a capacitor, and you'll notice this is a 0.47 microfarad capacitor, 10 times larger than we had on the high frequency side of the circuit. So frequencies 10 times lower can get through here, or well, let's just highlight that and say we've pointed that out. Okay, so our signal comes in through a 1K resistor and then through the capacitor right here. Now, also hooked into there, we have a 2.2K resistor going to the 9 line. And again, I use that little trick that I did with the capacitor on the low frequency side of just jumping that over together in there. And then in here, we have a U01 or 0.01 microfarad capacitor, a 10 nanofarad cap that comes in right here and also jumps up. And right in there, you can see that it's going to the high voltage line right in there. High voltage seems a bit of a misnomer for a 9-volt battery, but it's high enough to toast your audio equipment, as many students have discovered in the past. And so that comes in right there, and that's all hooked up to the base of the 3906 PNP bipolar junction capacitor. So let's highlight that, and that one is sitting right there in green. So now we've got two different filters working on this circuit. We've got a high pass and a low pass, and so we're getting rid of the lowest frequencies and we're blocking the highest frequencies, so only the mid-range frequencies come through and drive that transistor right there, and they give us flash coming out on the other side. Now, what I'm going to do is going to plug my DP scope in right here, and we can watch the frequency go right here. So much better when I'm just doing it for personal pleasure, not putting it on the internet and worrying about copyright. Okay, let's turn on my DP scope now. And there we go. That's my line doing the driving. I'm going to turn on channel 2 right here. And I'm going to take a look at the output to my high frequency LEDs right here. And they're on different scales, so I'll put them onto the same scale. And I'll bring them down to the same point right there. Alrighty. And so here you can see the raw signal coming in that's going out to everything on there. And this is responding quite well. And you can see the LEDs turn on when we get this sharp burst, and then they turn off right away afterwards. So when the blue line goes high, that's the LED turning on. And when this signal goes low, that's a strong burst of music coming in right there. So let's take a look at what that looks like if we come down to the low frequency side of the circuit right on here. And there you can see we had a whole bunch of high frequency bursts, tiny little bursts coming there, and no response on the LEDs right in here. But there we go. You see how this longer duration, bigger burst that came right in here of sound triggered the LEDs to turn on down at this end. Okay, and that's because this is a low frequency side of the circuit, so we need a longer duration signal in order for that to turn on. I just noticed one of the cameras has left me looking at the. Yeah, I'm actually moving here. I haven't suffered a massive, calamity and frozen in place, so not quite sure what happened on that. But the thing says we're still recording in here. Okay, so this is your color organ triple deluxe. It's a nifty little circuit. Now, there's a couple of interesting things going on right here with it, because so much of it is determined by the amplitude of the signal coming in right here. You can use the two buttons on your, let me just put this in here so you can see the whole thing. Two buttons on your DP scope. If you press and hold, you can control the volume. So if you turn the volume all the way down, let me replay that song. Okay, here we go. And so if I press and hold, one button, I turn the volume all the way down. Now with the volume all the way down, I don't get any response from the LEDs. If I press the other button and hold it, the volume comes up. And if I crank the volume all the way up, well, then the LEDs are on all the time because we're always running big signals in there. So uh, there is an ideal volume where you get the LEDs working properly in there. And that's your color organ triple deluxe. Okay, now works really nice if you've got the DF Player Mini hooked up to provide a bit of signal for you. And I should have given you the schematic for that already. And yeah, it seems to work really nice. If you're having a little bit of a problem getting the DF Player Mini to work properly for you, try putting a I don't know, 10, 100, something microfarad capacitor just between your plus 5 volt line and your ground, and hopefully that should work. When you set it up and start playing, the busy light right here should turn on. When you first turn it on, it might be on very weakly. If you make a mistake and hook your DF player up to 9 volts, you might end up toasting it. And if you do, you might toast your micro SD card inside of it as well. Don't ask me how I know that. Okay, well, it looks like one camera stopped recording me, so you can't see me kicking back in my chair saying, there we go. But there we go. Good luck building your color organ triple deluxe. There are far more sophisticated circuits out there, but it is pretty cool. Ultimately, what we're going to do once we get this all hooked up and running is we're going to be able to take it and put it together onto a perf board. And although I've gone kind of over the top on this circuit right here, uh, okay, I went way over the top, but it was a nice, peaceful, relaxing afternoon soldering things up. As you can see, I've got 2 color organs built in here for the left and right channel. I've got an amplifier built right in here using the monobox amp using the LM386, which we'll talk about a little bit later on. I've got my DF Player Mini, a couple of buttons on there to activate it. And what else have we got down here? We've got our Erie right down in here, and we've got a custom power supply, so I can run the whole thing off of 9 volts using a 7805 voltage regulator and some capacitors to provide a nice smooth 5 volt supply so I don't toast my DF Player Mini. Somewhere around 350 solder joints on there is my estimate. Right. That was probably enough. Let me find my mouse and press the stop button. Hope that helps explain the operation of high pass and low pass filters and the color organ triple deluxe. See you in class, if I can ever get moving again. Help, the camera has stopped.